Welcome to a lesson with Dr. Powell. Let's take a look at an example of of getting looking at eigenspaces or and eigenvalues for a matrix. We can compute its characteristic polynomial, cofactor expansion. Here, x minus 1 times this, and we just have 0, so that makes it really nice. Just that times the determinant of this part. You get x minus 1 cubed, actually, in this particular case. Now, that means the minimal polynomial could be anything from x minus 1, x minus 1 squared, or x minus 1 cubed. Now, if it were x minus 1 cubed, look what would happen. Like, the range of x minus 1 has to have dimension less than this guy, because if it had the same, it'd actually be invertible. And so x minus 1 cubed would be invertible too. That wouldn't work because we know it has to be 0. So it has to go down. And if it went down, let's see, and likewise, if you rewrote x minus 1 as a matrix according to a basis of the range right here, you'd have the same exact idea happening. So you have to go down a dimension every time. And in order to make it to 0 right here at this point minimally, you have to go down 1 each time. Okay, so now, well, let's just look at x minus 1 and see what we get. We get this, which the range is just multiple columns, the column space, has dimension 1 because these are just multiples of each other. So we've actually gone down by 2. So this can't happen, okay? And also know that x minus 1 is not the 0 matrix, which forces us, the minimal polynomial, to be x minus 1 squared in this particular case. Okay, so we know what the minimal polynomial is. We didn't even compute Smith normal form or a diagonal matrix or anything, but just by inspection, we determined what the minimal polynomial was, x minus 1 quantity squared. Okay. Notice that the range of x minus 1 is not the eigenspace of 1. However, in this case, and the reason, and this happens when we have this kind of thing going on sometimes when we have like just raised to a power and that's all we have. We don't get that because when we actually get the diagonal, really what's happening, so we can have a least common multiple of being x minus 1 quantity squared, we need to have 2 spots here because the characteristic polynomial is degree 3, and the product is the characteristic polynomial down that diagonal because it's determinant, and our row and column operations don't change the determinant. So we're looking at a situation like that, which means when we multiply by the matrix x minus 1, we're actually taking out of some of its own eigenspace. We're like making 0 happen here. So really, if we're looking at this subspace only, like this one right here, where that's the minimal polynomial at this point and not this one, then the range of x minus 1 just gives us information about the eigenspace portion that lives in here. But actually, there's more that lives over here, and there's a whole subspace that's determined by this column here that we get. And so eigenspace is actually split into 2 different locations. So the range of x minus 1 actually gives us part of it, but not the whole entire thing. Okay, so you know what? Instead of dealing with ranges, it's guaranteed. You can always look at the kernel. Kernel of x minus 1, so we can get that matrix right here. Look at the kernel. We can look at its reduced row echelon form rather quickly, realizing from here just up to here and using our technique. This is a non-pivot column. That gives us something easy, 1, 0, 0, 1, 0, 0, because we're just adding in the ones down the diagonal. That's great with our technique. Now here, the 1 comes, this isn't from, this pivots in the second column, so send this down to the second row and change its sign to -1, then you have the 1s going down. So this ends up being the basis for the eigenspace. So the eigenspace of x equals 1 in this case actually has 2 dimensions. Now this is the only eigenspace there is, and it doesn't fill out all dimensions here, and they don't always do that. And if this happens, then we actually will see that our matrix cannot be what's called diagonalizable. We'll talk about that in a later video. Thanks for watching.